So, basically, the topic today is all about how the conversational AI memory, how store the things, store the chat, store the past conversation. So, it will be very fun knowing all about this. So, when people talk to systems like ChatGPT, Gemini, or Claude, they often say, "It remembers what I say earlier." Technically, that's not quite memory in the human sense. What this model do is condition each new response on a window of prior text, a limited but carefully managed context. Understanding how state of the art large language model or LLM manage conversation context requires understanding three layers: tokenization and context window, the attention mechanism inside transformer, and internal memory strategies layered on top. Together, this gives the illusion of continuity across tones. So let's talk about the core concept. First, tokens. LLM LLM do not process words directly. They process tokens, subwords unit created through algorithms like byte pair encoding or similar varieties. A single word, a single word might be one token or several. Context window size is measured in tokens, not characters or sentence. The context window is the maximum number of tokens the model can see at once. Modern frontier models such as ChatGPT by OpenAI, Gemini by Google, and Claude by Anthropic supports very large context window ranging from tens of thousands to even over a million tokens in some configurations. But regardless of size, it is always finite. Second, attention. These models are built on the transformer architecture. The key innovation is self-attention. Each token in the context generates three vectors: a query, a key, and a value. Attention scores are computed between tokens, allowing the model to dynamically weight which previously token matters most when generating the next token. In simpler terms, when generating the next word, the model doesn't just look at the last sentence. It computes weighted relationship across the entire context window. That means earlier tones in the conversation can influence the current output, but only if they are still with the context window and receives meaningful attention weight. Third, decoding. LLMs are autoregressive. They generate one tokens at a time. At each step, the entire visible conversation, system instruction, prior user tones, assistant replies, it fade through the transformer stack. The probability distribution over the next token depends on all tokens currently in context. This is no persistence hidden state across conversation. Each response is computed from scratch over the provided context. So, architectural level approach. Architecturally, a multi-tone conversation is typically represented as a single concatenated prompt. It may include spatial roles tokens like systems, users, and assistants. From the model's perspective, it's just a sequence of tokens. Attention computation scales roughly quadratically with context length. If you double the context, computation and memory cost grows significantly. This is why expanding context window is not trivial and expensive. To handle longer conversation effectively, each model may use optimized attention variance, such as sparse attention or sliding window mechanism. But the fundamental constraint remains. The model can only directly attain to tokens currently in this window. When earlier when earlier tones falls outside the window, they are effectively forgotten unless some external strategies preserve them. So practical memory strategies. This is where engineered memory systems comes in. One common strategy is summarization compression. When a conversation gets long, earlier tones are condensed into a shorter summary that remains within the context window. This trace verbatim recalls from semantic continuity. Another approach is incremental memory. Important facts such as user preference are extracted and stored separately, then reinjected into future prompts. This is structured memory rather than raw transcript replay. The most powerful method is retrieval augmented generation or RAG. In RAG systems, conversation history or external documents are embedded into vectors and stored in a database. When the user asks something, relevant chunks are retrieved using similarity stores and inserted into the context before generation. This extends effective memory far beyond the model's native window. Now, we must distinguish in-model memory versus external storage. In-model memory refers only to what exists inside the transformer's current context window. It disappears when the conversation resets. External memory system persists outside the model. In database or vector store and are selectively reintroduced. This separation has privacy implication because raw conversation data may be stored externally for retrieval. System designers must implement strong data governance and encryption. From a latency perspective, RAG introduced additional steps, embedding computation, database search, and prompt reconstruction that increases response times enables scalability. Cross-model comparison across ChatGPT, Gemini, and Claude, the fundamental mechanism is the same. Transformer-based autoregressive model with large context window. Difference typically appears in scale and tooling. Some models emphasize extremely large context window. Others emphasize hybrid system tightly integrate with retrieval pipelines or tool uses framework. But none of this system poses persistence memory by default in the human sense. They rely on prompt reconstruction plus engineered memory layers. So, in summary, conversational continuity in modern LLMs is not magic memory. It's structured conditioning over tokens inside a bounded window powered by self attention. Beyond that window, beyond that window, persistence requires summarization, extraction, or retrieval systems layered around the model. The future of conversational AI is likely not just larger context windows, which are computationally expensive, but smarter memory orchestration, deciding what to compress, what to store, what to retrieve, and when. So, when an AI remembers, what is really doing is attending. So, when an AI remembers, what it is really doing is attending carefully, mathematically, and temporarily to tokens that engineers have decided to keep within reach. So that's it for today, guys. Have you understood something about how really the AI models have the knowledge about our previous conversation? So that's it for today, guys. I'll be meeting you in the next one. Bye.